Today, we're going to tackle a classic machine learning algorithm, the support vector machine, or SVM, and it all starts with a very simple question.
So, imagine you've got two groups of data points. Your job is to draw a line that separates them. Seems pretty straightforward, right? A line like this one gets the job done. But here's the catch. You could draw infinite lines that separate these points. Is this line better? Or what about this one that's kind of hugging the blue dots? How do we find the one single best line? The one that's most likely to correctly classify new data it's never seen before?
That is the exact puzzle that support vector machines are built to solve. And in the next few minutes, you're going to get the core intuition for how they find that perfect, most robust boundary.
The secret to the SVM isn't about drawing a line at all. It's about paving a street.
So, here's the mental model. Forget about a thin line. Instead, I want you to imagine we're trying to fit the widest possible street between our two groups of data points, with one rule. No data points are allowed on the street itself.
Here's how that works, visually. You can start with any line. Then you start expanding it, making it wider and wider, creating a street. You keep expanding until the edges of the street just barely touch the closest point from each group. That's it, you stop. The center line of that specific street, the widest one you could possibly make, is your optimal boundary.
And that's really the whole game here. It's not just about separating things, it's about creating the biggest possible buffer zone between them. Now, why does this even matter? Well, a wider street means a more robust model. Think about it. The boundary isn't biased towards one class or the other. It's in the safest possible position, which means it's much more likely to classify new, unseen data correctly. It generalizes better.
Okay, so you've got the widest street intuition down. Now let's connect that analogy to the technical terms you'll actually see when you work with SVMs.
First up, that center line of our street, the formal name for that is the hyperplane. You know, in 2 dimensions, it's just a line. In 3, it's a flat plane. And in anything higher than that, we just call it a hyperplane. It's the decision boundary.
And the width of the street itself? That's called the margin. The entire goal of an SVM algorithm, its whole purpose in life, is to find the hyperplane that creates the maximum possible margin.
Which brings us to the most important term of all, support vectors. These are the specific data points that sit right on the edge of the street, the ones that stop the margin from getting any wider. They are literally the vectors that support the hyperplane. And here's the crucial part. These are the only data points that matter. You could delete every other point and the hyperplane wouldn't move an inch. But if you move a support vector, the whole street has to be redrawn.
Now, this widest street approach is fantastic when your data is cleanly separable. But what happens when the real world gets messy?
Yeah, take a look at this. We've got a cluster of blue dots completely surrounded by green dots. There is no straight line, no straight street that can separate these two classes. A simple SVM would just fail here. This is where SVMs have a really clever ace up their sleeve called the kernel trick. The big idea is if you can't separate the data in its current dimension, maybe you can project it into a higher dimension where it becomes separable. Imagine we could just reach in and lift those blue dots up off the page into a third dimension. Suddenly, from that new perspective, it's super easy to just slide a flat plane right between the two groups. The kernel trick is just a really efficient mathematical shortcut to achieve this separation without actually doing all the heavy computation of moving to a new dimension. And you can do this trick in different ways, using different kernel functions. The most popular one you'll run into is called the RBF, or radial basis function kernel. It's incredibly flexible and can create very complex decision boundaries for you.
So when would you actually reach for an SVM in your day-to-day work?
Well, a good way to think about it is to compare it to something like logistic regression. Logistic regression looks at all the data to figure out probabilities. An SVM has a totally different philosophy. It ignores almost all the data and focuses only on the most difficult points, those support vectors, to define the decision boundary. This unique focus makes SVMs especially powerful in high-dimensional spaces, where you have a ton of features.
Because of that, SVMs have a long history of success in really complex problems. Think about text classification, where every single word can be a feature, or bioinformatics and gene analysis. For a long time, SVMs were the absolute state-of-the-art for tasks like recognizing handwritten numbers.
So, if we boil it all down to one sentence, an SVM finds the optimal boundary between classes by maximizing the margin, or the widest street between them.
The key takeaway today is that an SVM's power comes from focusing only on the hardest points to classify. And that leaves us with a final thought. If your model is defined entirely by the edge cases, what does that tell you about the importance and the potential danger of outliers in your data?